Thank you for being here. I'm here because of your courtesy, so thank you very much for this. Also, I met you first time 2 years ago, so I must say that I become a regular participant because I'm honored so much to participate in this symposium. My topic is the AHP phenomenon of rank reversal demystified. And I would like to concentrate on something what was troublesome to scientists for many decades. And here I have some basic summary of that, what was written as far about different phenomena about the AHP. And actually, this is a summary and the time is short, so I think I will not discuss the details of this phenomena that were discovered during these years, but I will focus on something that very much interested me actually 2 years ago when I spoke actually with Enrique Mu during this symposium, and he triggered the question that gave me to thinking, and it was about the relation between the consistency of pairwise comparisons and the errors, actually possible errors of priorities within the priority vectors. And that's why I thought about this example that was presented first time in 1983, I guess, by Belton and Geer, when they came with this model consisted of 3 criteria and 3 alternatives that were compared. And basing on some comparisons, they came to the conclusion that the final priority vector in such an example was as follows, which is the 0.451 and 0.470 and 0.099, which gave the final ranking of the alternatives from best to worst as BAC. And I don't know how familiar you are with this example, but basically all of us who are interested in this phenomenon of AHP practically know everything about this first example of this phenomenon. So that is to say that this was based actually on fully consistent comparisons within the pairwise comparison matrices, and they introduced today's model in order to show something that I also would like to present, that if they added the 4th alternative, actually not changing the judgments among the earlier ones, the final rank of the primary of the vector changed a little bit, because as on the beginning we had the final ranking of the alternatives from the best to worst as BAC, and with the introduction of the 4th alternative, we have ABDC or a DBC, because B and D in this model actually is ranked as the same. And on that basis, actually the heated debate was started, that should it occur, should it not occur, what is the reason actually that such change occurred, because only the alternative was added to 3 other alternatives without any changing in preferences concerning the previously introduced 3 alternatives. And actually that got me into thinking, what is the reason actually, and is this true evidence that the changes in the ranking really occurred? So I try to think that from that perspective of the simulation and the model that I introduced. And before I tell you something about the model, I would like to start from the simple example that the model actually follows. So if we consider the true priority vector, which can be based on true measures of objects. Thomas Sati did that on figures. We can do that on any other objects, measuring their weights, size, or whatever. This is arbitrary vector that I propose for this particular example. And on the basis of this vector, the pairwise comparison matrix is derived, which looks like this one. And then that matrix is somehow rounded. Why it is rounded? Because we consider that this particular matrix, which represents the previous one, is produced by a hypothetical decision maker, and this decision maker, is very trustworthy and is able to express his or her judgments very precisely, at the same time being still somehow limited by the necessity of expressing judgments on a scale, which must be used in AHP. It can be, of course, the original scale of Thomas Sati, which is utilized here, but also there are many other scales with some advantages and disadvantages, which also limit somehow the decision maker in this process. So this scenario assumes this is the Sati scale is used here, and also that the entries of this previous pairwise comparison matrix is rounded to the scale, and then entries are made reciprocal, which is the principal condition for each pairwise comparison matrix used and applied in the AHP process. And on the basis of this pairwise comparison matrix, it is possible, of course, again, to calculate the priority vector with the original method, eigenvalue method, or each known other method, because there are also a few in the literature, like, for example, the geometric mean method. And in this case, because you can notice that this pairwise comparison matrix is perfectly consistent. So each actually applied method will give the exact the same priority vector. I gave you an example of right eigenvalue method and geometric mean method, and the priority ratios given here are exactly the same. The consistency index is equal to 0, and on the basis of these two priority vectors, actually, this one and in the original, let's say the generic one that was the primary priority vector for the example, we can calculate some deviations. And the basic deviation which can be calculated here is the average absolute error given here with this formula. And on this example, we can see that we can have some small deviations between the original generic priority vector and this vector that is calculated on the basis of the pairwise comparison matrix produced by this hypothetical decision maker. And that triggered my interest, and I decided to design the simulation scenario in the software Monte Carlo simulation that could simulate actually thousands of such examples and measure such small deviations between the priority ratios within the priority vectors. And you can believe or not, but in this example given by Belton and Gear in 1983, we have this order of the ranking that cannot be actually determined indisputably, because for 3 alternatives, the median average absolute error for simulations that were based on 50,000 similar matrices as that one in the example, gave me an error of 0.0138389. And if we multiply that by 2, we will receive the error of 0.0276778, which is, as you can see, a little bit bigger than the distance between the first and the second here priority ratio. So this actually rating, basing only on the median value of all average errors, indicates actually that can simply change. So it can be BAC, but it can be also ABC without any problem actually. So my opinion is in this case that this example is based on a little bit fallacious assumptions. So this is not evidence for 100%, because we always in AHP take these priority ratios in the priority vectors as given, as determined, as they are. So if we have like here, let's say, let's say priority ratio equal to 0.451, it is discussed and examined as 0.451. But in my opinion, it should be treated as the estimated value with some error, with the error which probability can be, of course, calculated on the basis of simulation. So I also calculated many other possible statistical errors, like, for example, mean average absolute error, and it is a little bit bigger, of course. As you can see, I multiplied again this error times 2 to show that for sure, let's say, we can be consider these priority ratios as certain when the distance between them, it should be bigger than 0.1. And also I calculated for 3 alternatives the median value of maximal deviation from average absolute error. And again, it is a little bit bigger. I also calculated on that basis maximal absolute deviation for a priority ratio as median and mean value of these measures. And as you can see, these are like 0.05 or 0.16. And on that basis, I totally agree with the creator of this methodology, Thomas Sati, who said once that he doesn't want to falsify, for example, his AHP. He was convinced that further falsifying AHP can lead to worse scenarios, actually, and worse assessment. And I totally agree, because I think that the AHP is already falsified, because these numbers cannot be treated as determined, but only as the estimated, and estimated with the certain portion of some error which can be calculated. So the example of these two authors, like Belton and Gear, in my opinion, is not convincing that the rank reversal phenomenon is at all evidence in AHP. So I propose the conclusions that the evidence of the examination indicates actually that priority vectors derived from both consistent and inconsistent pairwise comparison matrices are fuzzy and should not be considered as set, but only as estimated with certain level of probability. Hence, any evidence showing rank reversal in the AHP models, which is based on assumptions about the determined value, should be considered as erroneous. And that's all. Thank you very much. If you have questions, of course, I will be gladly to answer them.
Do you have any questions? So, Pawel, I don't know if you are aware of the publications in the subject when they first came out with that example from Belton and Gear. The example was proposed by, they were using values, not just empirical comparisons, if you recall, but in a table where you have values, actual numerical values of measurement, from which the pair comparisons were obtained. So Pat Harker and I published a paper in Management Science showing that the reason why the reversal happened was because the weights of the criteria, it was erroneous to assume that the weights of the criteria were equal. Actually, there was a loop, the approach to do that. Later on in 2012, I think Tom and I published a paper in Social Choice and Welfare, where we showed that if you have what they call row dominance in a matrix, when you introduce a new alternative or deleted, you don't have rank reversal. But that happens with a single matrix. When you have multiple criteria, like you have in this case, the reason for the reversal happened because the criteria weights are not the correct ones. So that's in addition to the idea that if you have to incorporate another alternative, the only time that you can say actually that the reversal should not happen is if you knew the values of the alternatives under each of the criteria, actual values from a scale which is not a normalized scale. If you know that, then you know whether the reversal should not have happened. But otherwise, if you decide that you want to keep the criteria the same, then the results are the results as you're saying. So the reason why they said that there was a counterexample is because they assumed that the alternatives were measured in criteria and they had actual values, 9, 1, 8, whatever they were, the numbers, from which they used the pair comparisons. So they knew that if you added the criteria, the alternatives under each criterion, you have weights for the criteria. And if you added the columns, you get the criteria, the values of the alternatives for each of them. And so they knew what they wanted to get, but because they had the wrong criteria weights, they got the wrong result. And they call that a counterexample. But later on, I can assure you that Valerie Belton actually in a MCDA conference retracted herself, saying that the example was erroneous. So of course, if you have multiple criteria and you add an alternative, right? If you don't change your criteria weights, it's possible that you have what they call rank reversal but if you have row dominance, if you eliminate the row or the column of an alternative of the matrix, you will not have rank reversal. But with multiple criteria, if you don't change the criteria weights, you're stuck with it. So I'm with you.
Thank you. I'm exactly.
A long explanation for the same thing.
Okay.
And I believe that Bill Wedley, who's in here, actually you wrote also a note about why that was happening, change in units, remember?
Yeah, exactly. Tomorrow, the presentation will be tomorrow of Wedley.
Yeah,
I read that. Yeah, I totally agree also with that.
And I believe that actually Tom and I wrote a reply to that paper in, I don't know if it was in Omega, something like that. I can't remember exactly what it was. But. Any questions?
I can see that on the chat there's a question, but I don't know.
Wait, let me see what let me see
Is
what
it is it to me? Yes.
Sergey Kadenko is talking. Is it a conflict between the number of objects estimated and the limitations of the scale?
And if I correct understand that question, actually the scale is the limitation causing the priority ratios shouldn't be treated as determined. I think that it is one of the three actually limitations: scale, reciprocity in the pairwise comparison matrices, and the human judgments. We can be also emulated by the perturbation with some random factor of the pairwise comparison matrix. And I add actually all of them to my simulations, and I still think that because of them, actually, because of those limitations, we should treat these priority ratios as the estimated value and not as determined ones. That with some certain level of certainty, let's say that it's not given but only estimated. And if we consider the priority vector in that way, we will be more conscious about the measurement of consistency of human judgments also. Because as Thomas said once, that we cannot take it as granted that if the matrices and the decision maker is fully consistent, the priority vector will really give the accurate results, because sometimes the small inconsistency causes better estimation, and it was also actually proved in one of my papers that sometimes we need this inconsistency in judgments in order to make better results. It's not always like that the fully consistent matrices are the best, because sometimes fully consistent matrices can give worse results, which is fantastic actually about the AHP.